Okay, calendar. Our calendar says we're doing chapter 6. We're finishing up chapter 6. We started chapter 6, now we're going to finish chapter 6. And we will be good. Okay. How is chapter 6 going for everybody? Have you guys had a chance to get started on it? Let's see, what is chapter 6 all about anyway? Can't remember how far we got in chapter 6, so we got to go take a look. Circular motion and gravitation. Oh, I think we got all the way through chapter 6 actually. We went through it rather quickly, but we did get through it. So it's uniform circular motion, gravitation, and so we're looking for things that are involving stuff like angular rotation and so on, just basic circular motion. What is this? Oh, they actually show you. It shows. You'd like to be one of the people out there waiting for that thing to come flying at you. It's kind of crazy. Gotta replace your divot. Anyway. Okay. So the hammer throw. They're trying to help us figure out where this thing is going to go. If we want it to go towards the X, where do we want to let go of it? When do we want to let go? Anybody have an idea? The key to this problem is to think that at any point on this line, which direction is the ball going? At any point on this line, the ball is going at a line that is tangent to the circle at that point. So a tangent line is a line that comes through and only touches the circle at one point. So at point G, this is a vertical line right here. Point C, it's a vertical line. At point A, it's a horizontal line. Point E, it's a horizontal line. And D and F and H and B, they're all these diagonally kind of lines, right? So if it's going to hit X, it has to be released at point E because that's the direction it's going right there. It's going towards the X right there. So if we let it go, then we won't be pulling it into the circle anymore, and it will go in that straight line. If we let it go at point F, it's going to go off in this direction. If we let it go at point G, it's going to go off in this direction. You have to let it go at point E for it to go and hit that X. Now, probably the most common error made with this is either, well, the two most common ones are the F or the G. The F because it's between the X and the person throwing, and the G because it's on the front side of the circle. But neither of those is correct. If you let go of it at G, it will go sideways to the left. And if you let go at F, it will go off at this angle to the left. So, important stuff. wrong with that? What am I doing? I'm not enrolled in this course, so what? Who cares? What is going on? Chapter 6. So the hammer throw, rearranging equations, we know how to do. Accelerations, right? 9.3 meters per second. And the radius of the circular path is 6.11 meters. Now this is something that I would recommend that you kind of think about. And that is the difference between linear physics and rotational physics. In linear physics, we had this, we said that we were going to have some kind of displacement, displacement we called x, right? But in rotational physics, we don't have an x, we have, so x is a position, displacement is delta x, right? Delta x, which is equal to your final position minus your initial position, right? In rotational, we talk about rotation, so we talk about the angle theta that you're at, where theta is measured from some axis, so maybe from the x-axis, theta is measured. And then you can have a change in angle. You start at one angle and move to another angle, rotate to another angle, where a change in theta is your final theta minus your initial theta. Right? In the linear realm, if you changed your distance, if you changed your position rather, and you did it in a certain amount of time, delta x over delta t, then we called this velocity. Your velocity was your change in x over time. In rotational, we have a change in theta over time. And we called that omega. If we go back to 6.2, we had this relationship between. Well, let's go back one more. Right here. If we go back to 6.1, we had this delta theta here, and we talked about radians. We learned about radians, but we had this angular velocity omega, and we made this relationship between the linear velocity or the tangential velocity, or the speed along the edge of the circle, with the angular velocity. And that became quite useful. Where'd my whiteboard go? So that relationship looks like this, where if you want to look at we call this tangential velocity, usually, V tangential, which is like the speed on the edge of the circle. And that actually can be calculated if it's a constant radius and a constant angular velocity by taking the radius of the circle that you're on and multiplying it by the angular velocity that you're at. You multiply r times omega, you get the tangential velocity. So that's quite useful. And this one we might kind of put in between because it has a little bit of both of these things in it. So if we put that kind of in between, it's kind of like a bridge between the angular and the linear. V tangential equals r times omega. And in fact, in a previous, in the next section, they actually talk a little bit about this as well, I believe, where there's a relationship between the linear and the rotational in distance as well. If you go a certain angle along the circle, theta, and you multiply that by r, then you're going to actually get the path length, which they call delta s, but that's the arc length along the circle. So that's another thing that connects, this connects the linear side to the rotational side, linear side to rotational side. So it's good to kind of start thinking of movement in these terms. There are linear things, there's these bridge things, and there's rotational things. We'll come back to that a little bit more in a later chapter, but that's good for now. So if you're in this machine that spins you around and around and around at this constant radius, and they're going 9.3 meters per second, that would be that tangential velocity. That's their speed along the edge of the circle. So that's equal to r times omega. And they tell us the radius of the path is 6.11 meters, so we can actually calculate the omega. But we can also calculate the centripetal acceleration, because there's one more thing that they tell us in this chapter, and that comes along right here in the next section, when they talk about what kind of acceleration causes things to move in circles. And that is the centripetal acceleration. If you have the tangential velocity and the radius, you square the velocity, divide by the radius, and that will give you your centripetal acceleration. That's right there. Once you know your centripetal acceleration in meters per second squared, then you just divide it by g, which is 9.8, and that tells you how many g's you're going to feel. Maybe 2.3, it might be 5.8, whatever. Right? And so on and so forth. So this is a similar question. And then we get down to the part we talk about gravitational forces, and we talk about Newton's law of gravitation. So that's after this centripetal part here. So Newton's law of gravitation, which tells us the force between two massive objects is equal to g, which is this gravitational constant, times the masses of the two objects divided by the distance squared between the two objects. Let's see, need to go back here. So anyway, this is Newton's gravitational law here, and with each one of these things, there's a different mass in each one, but they're not telling us what the masses are, and they're not telling what the distances. They're just giving us some different scenarios, right? They want to know, where is the force the largest? Well, the easiest way to do this is to just plug these things into that equation and see which one is going to give you the biggest number. So for this first one, you would have big G times big M times 2 times little m divided by d squared, right? And each one of the equations is going to have a big M in it and a little m in it and a d squared in it. What you got to do is figure out which one has the biggest number out in front, from like the 2's and the 2's here. You know, there's these 2's in different places. Which one's going to have the biggest, which one is going to have the biggest number out in front? I give you a fair warning, when you put the 2d into the equation, you have to square the 2 and the d in the denominator. If you don't square the 2 and the d, you might get something wrong on this one. And then some more gravitational problems with just constants, just variables without any numbers, some multiple choice action, some more multiple choice. Here they tell you how much force it is, and they tell you that the distance increases by triple. So if the distance increases by triple and it's 1 over distance squared, what's going to happen to the force? If force is dependent on 1 over something squared, and that thing that is squared increases its size by 3 times, what happens when 3 is squared? What does it become? It's 3 squared. It's 9, right? So what happens in this case is that instead of this thing just dropping by 3, because when you separate it 3, if you separate two objects by triple the distance, you would expect the gravitational force to go down. But instead of going down by just 3, it goes down by 9. Okay? Because of that 1 over distance squared. And this here is another one where you have to figure out what is that going to look like on a graph. If the force goes down by a factor of 9 when you go out by a factor of 3, does it look like this, 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 or this? Not so simple. I've given you too many choices on that one. That's too easy. Why do I give you 7 attempts on these things? Those are supposed to only be 2 attempts. I'll have to fix that. And then, of course, the problem with the car. That's really the only challenging problem in that we did this one. Did we actually work through this problem? I think we did. But it's done also in the book. So does anybody have any particular problems that they have a particular question on from this chapter? No particular question? All right, if that is the case, then let's move on to chapter 7. Chapter 7 is due on Friday this week, so you'll have the rest of the week to do it. And we'll go through chapter 7 today, finish it up on Wednesday, and start chapter 8 probably Wednesday. Let's see, what is chapter 7 is energy. Chapter 8 is momentum. Yeah, we'll probably be fine. If we get done a little, we might get done a little early. 7, 8. And if we do, we'll just push some things up a little bit and see if we can't make some more room there at the end of the semester. That's fine. All right. So we're going to move on to chapter 7. And many books in physics actually start with this chapter. And the reason is because the math is much easier. And you can do a lot of the same kind of problems with easier math. I prefer not to do this chapter first because I think it's instructive to do the hard work first and then learn that there's an easier way to do some problems. But in this chapter, we're going to talk about what is energy. We haven't talked about energy yet. We've only talked about essentially kinematics, movement, and we've talked about force, which is what we call dynamics. Now we're going to talk about energy, which is related to movement and related to force. So it's definitely part of those things. And energy, of course, is quite important to us in many ways because it's how we do things. With energy, you have to have energy to get things done in this universe. So they have this picture of the wind farm in Iowa, which is kind of ironic because 10 years ago, wind farms were all the rage. Everybody was building up windmills because we were going to have all this free energy. And now everybody's taking wind farms apart because they didn't listen to the scientists in the first place. And this happens all the time in politics. The politicians thought that, we were going to destroy our Earth and that the glaciers were all going to go away and the oceans were going to rise, and they called it global warming. And then for the past 10 years, the Earth started getting cooler. And the reason that they were freaking out is because the 10 years before that, the Earth was getting warmer. But they failed to tell anybody, the media failed to tell anybody that the Earth goes through cycles like this all the time. The scientists knew this all along. The amount of temperature that they were measuring was only fractions of degrees. We're not talking about anything extreme here. But they said if we keep burning fossil fuels, this is going to ruin the Earth. And granted, we do need to figure out something besides fossil fuels. First of all, they're not very clean, and second of all, they're going to run out eventually. But wind power is not a very good option, honestly. It's extremely difficult to harness wind power, just because it just is. It's just wind blows these things over all the time. People are falling off these towers all the time, and they're maintaining them. It's just not the best idea in the world, and they're just super expensive. The energy from these wind towers costs about twice as much as it does from normal power plants, and people were just not willing to pay that much for electricity. Go figure. So I would suspect that in another 10 years that there won't be any more windmill farms out there, that you'll see them all dismantled and gone. And then another 10 years after that, they'll start building them again. It's just because they started building them back in the 70s was the first time. They built a big, huge windmill farm outside my town, and it just kind of died off and went away, and they took it all down. Then they've put up a new one in that same place about 10 years ago. They'll take it down and put up a new one, and whatever. This is about a 20 to 30 year cycle. But the important thing that we need to realize about this is that we do use a lot of energy, and every person that is born on this earth is using energy, and the population of the earth is growing at a fairly constant rate. Nothing to really worry about, in my opinion. This earth, it's well known. It's not even something you can argue about. This earth can probably support 1,000 times more many people, 1,000 times the people that it does now. So we have about 5 billion. This earth can probably handle, about 5 trillion people. It's just that big. It really is. People forget that we are only populating a very small portion of this planet. And it's not, I think it's less than 1% of this earth actually has people on it. Less than 1% of this earth actually has people on it. So it's not really crowded yet. Nothing to really worry about at the moment. But we need to talk about what energy is. So what is energy? It's actually a fairly difficult concept. It took scientists, physicists, a few hundred years to actually figure out what energy is and to understand the mathematics of energy. And the reason for it is because there are many things that look the same but are not exactly the same. You've probably heard the word momentum before. Momentum and energy are very similar things physically in the world. They manifest themselves in very similar ways, but they're not the same thing. And it actually came down to one scientist who was a very unlikely scientist at the time, because she was a woman, and it was in France in the 1700s, 1600s. Anyway, a time when women just were not allowed to be in science. And her name was Émilie du Châtelet. There you go. She was a noble woman, which means she had money and property and the ability to do anything she wanted as long as She didn't upset anybody that was in power, but she wasn't satisfied with that. She wanted to be a scientist and a mathematician. And her father and her brothers were all scientists and mathematicians, and they actually encouraged her in this, which again was really quite different. Not many men encouraged women in science in those days, but they did, and it's a very good thing that they did, because she was one of the only scientists at the time that was able to figure out energy. And she did a lot of studying of other people's experiments. She did a lot of her own experiments, and she didn't actually get credit for her work right away, because her father and her brothers didn't want people to disregard her work. And so this is actually well documented. They know that the brothers and the father weren't trying to take credit for her work, but they did start publishing her works under their names to start. And then slowly they tried to put her name into the works in ways that people would accept her, and eventually they gave her credit for everything that she did. And that actually worked out fairly well. I think the thing that really changed the world for her is that she became very, very good friends. Some people say that they were probably even romantic with each other, but she became very good friends with what's his name? He's probably here somewhere. Voltaire, yeah. So Voltaire, who of course was author and philosopher and all kinds of things at the same time, was very influential at that time in that period of history. And because of her association with him, her work was actually given more credit. She didn't have to fight off the men who were going to try to take credit for her work, because nobody wanted to go up against somebody as powerful as Voltaire, who had friends in high places. So she was able to kind of stand on her own 2 feet with the help of some people that really thought she deserved that chance, which is great. So this is actually not very, very long after Newton. We're talking just 100 years or so, a little bit more than 100 years maybe. So that's really amazing, actually. Not many women at that time were in any kind of science. It was really rare for them to be in physics or mathematics. Biology was a little bit different, but not much. But she was one of the early scientists that were a woman. There was a woman that actually got credit for her work. So that's kind of cool, kind of interesting. Anyway, one of the things that she did she did this experiment where she was dropping masses into clay. And as they fell into the clay, she was measuring different things about them. And one of the things she measured is how deep they burrowed into the clay, how big of a hole they made. And that actually led to one of our biggest understandings about what energy is versus what momentum is. So, what is energy? Well, first of all, let's talk about what we call work. Work is one kind of energy. There are many types of energy. Work is one kind of energy. And work is the amount of energy that is transferred to an object when you apply a force to it. So when you're pushing on it or pulling on it and you make it move, you make something move, you're giving it some energy. And the amount of energy that you give it is the work. And it's equal to the force that you apply times the distance that the object moves in the direction that you push it. So for example, if you have a lawnmower like this and you're pushing it, you're actually pushing along the handle. You're pushing this way, and that's just because the handle is pointing this way. But part of your pushing is going into moving the lawnmower in the direction, or pushing the lawnmower in the direction that it's actually going to move, because it's going to move horizontally, right? So in this case, you actually have to take the force times the cosine of the angle between the force and the displacement. So if you have a displacement vector or the change in position vector and the force vector, and you take that angle between them, multiply by the cosine, then multiply by the actual force that you push with, you'll get the amount of force that pushes in the direction of the movement. So work is equal to force times distance times cosine of the angle between the force and the distance. Plain and simple. So how much force, well, how much work is done if you're carrying a briefcase by you're lifting the briefcase upward like this, and you're walking forward like this? How much work are you going to do in this situation? If it's force times distance times the cosine of the angle theta. In this case, the angle theta is 90 degrees, the cosine of 90 is 0. So how much work are you going to do? None. You don't do any work if the force that you apply is 90 degrees to the movement that you're moving something. So in this case, you're not giving the briefcase any energy, really, as far as with your hand. Now, your feet are giving the briefcase energy because your feet are pushing backwards on the ground this way, the ground is pushing forward on you this way, and you're moving the briefcase this way. So you're doing work with your feet, but not with your hand. Okay? Doesn't mean that your hand doesn't get tired. Doesn't mean that your arm doesn't get tired. It does. But it's not because of work that you're doing on the briefcase. And then there's another situation that's kind of interesting. If you walk up the stairs with the briefcase, then you've got a force times the cosine of the angle between the force and the distance that you travel here. And you multiply this littler force times this longer distance to get the work. But if you just lift it straight up the stairs with this force and this distance, or drop it down the stairs either way, with an electrical generator, you get a longer force and a shorter distance, but shorter force, longer distance, longer force, shorter distance, it actually doesn't matter. It's going to be the same amount of work, because in the end, all you've done is lifted it to a higher level, right? So there are many situations where even though you take a different path to get there, you do the same amount of work. So that's something you have to be aware of, because that can pop up in these kinds of equations all the time. But the interesting thing that we haven't even mentioned yet is that on the left-hand side, there's no bold-faced letters. On the right-hand side, we have a vector force, we have a vector for distance, but the left-hand side, there's no vector. Energy is not a vector. It doesn't care about direction. There can be negative energies. You can do negative work. For example, if I do work on something, I'm going to give my energy to it, right? But if I do negative work on something, it's like it's doing work on me. It gives me energy, or I take energy from it, right? So work can have a positive or a negative effect. In general, positive work increases in energy on an object. Negative work decreases energy on an object. Negative energy, positive energy. So let's just do a really simple example with the lawnmower. So we're going to exert a force of 75 newtons. Remember that this 75 newtons acts along the handle, because the force always acts along through an object in a pushing or pulling scenario. So the force is going through the handle, so it's at that angle, and they tell us the angle is 35 degrees, and the lawnmower is going to move 25 meters on level ground. And we want to know how much work is being done. Well, first of all, we should know that when we multiply force times distance, we're going to get newtons times meters. Newtons times meters are a unit we call the joule, named after a scientist who did some experiments with energy, lots of experiments with energy. So 1 joule of energy is 1 newton of force pushing something for 1 meter, right? So it's not a lot of energy. Right here they say a 100-gram apple, if you lift it about a meter. So like one of these remotes, or like a little power block like this, if you lift that from the ground to here, that's the energy. If you drop it from here to there, that's about that much energy. Put your hand on that. You'll feel it, but it's not going to kill you. You know, it's not a ton of energy, but it's definitely noticeable. So in this problem, they want us to calculate the energy, and they want us to convert it to kilocalories. Now, kilocalories is another unit of energy. It turns out that 1 food kilocalorie, so 1 calorie, which is one food calorie, which is 1 kilocalorie, is equivalent to 4,186 joules. So when they say you should when they say your drink has 25 calories, that's equal to 25 times 4,000 joules, right? That's 100,000 joules of energy. Is 100 or 25 calories of food calories. So anyway, let's do the math first. We have our 75 newtons, 25 meters, and the angle between them is 35 degrees. Multiply it out, we get 536 joules, 540 joules in this approximation. To convert that into calories, we are going to divide that by 4,186 joules, because there's 1 calorie per 4,186 joules. So that's 0.367 calories, or 0.367 kilocalories, which is 0.367 food calories. So pushing a lawnmower 25 meters will burn 1/3 of a calorie. Kind of frustrating, isn't it? In fact, doing something like riding a bicycle or jogging or things like that do not burn nearly the amount of calories that people think they do. It's very few calories, in fact. Most of the calories that we burn every day in our bodies are actually burned just by living. Our heart beating, the heat going through our bodies, breathing, walking, blood pumping, all these things that happen in our body, even thinking burns calories. But all these things that are happening inside of our bodies just on a regular, just normal stuff outside of exercise, what burn most of the calories in our body every day, particularly the heat. The amount of heat that we do, is the amount of heat that we give off every day is where most of our energy goes, believe it or not. Most of that energy is turned into heat. And believe it or not, none of that energy is turned into weight. Weight is not something that is the weight that we gain or that we lose is based on two things, essentially. We eat food in, we bring in food, and then we have waste that goes out of our body. But then the big thing that contributes to our weight, well, also water is included in that first one. But the other thing the big thing that actually contributes to weight is breathing. We breathe in oxygen, and that oxygen goes into our body and makes molecules. We use it to make molecules, along with other things that we eat. And then when we breathe out carbon dioxide, and that's where we lose weight, is by breathing. That's why aerobic exercise is so important for weight loss, because in aerobic exercise you breathe a lot, and that's where your weight loss comes from, is from breathing out. So, kind of an interesting. The energy part just goes into building and breaking molecules. That's where the energy is. The more molecules you break, the more CO2 you make, the more you can breathe it out and lose weight. So, work is this one type of energy that allows us to move things or to be moved. It always has to do with movement. If you don't move in the direction that you're being pushed or pulled, then there's no work involved in. But it doesn't mean there's no energy involved. There's lots of other kinds of energy. So we're going to talk about how we deal with all these kinds of energy. So here is a graph called a work. This is this is actually a force distance graph, but it's also sometimes called an energy graph, because if you put the force on the y-axis and the distance that you move on the x-axis, then the area underneath the line that you make as you move from point A to point B here is going to be equal to the work that you've done. So the area under the curve is the work. If you're increasing your force and changing distance, then it looks like a slanted line instead of a straight line. This is just moving a distance at a constant force. We're increasing the force as we move further and further and further. In this case, you have to think in terms of what is the area underneath a shape instead of underneath a line. This is just, height times width. This one is going to be more like a triangle where you have to maybe do something different. And there are many situations where we'll use that. Here is an example where we're going to apply a force of 120 newtons on a box, but there's friction, the friction backwards. So what force do we use, this one or this one? Well, This force is going to add energy to the box, so it's going to be a positive work on the box. This is going to be a negative work on the box because it's going to take energy from the box. So we have to add those two forces together. So you take the net force times the distance times the cosine of the angle. In this case, the force and the distance are in the same direction, so there's an angle of 0 between them. The cosine of 0 is 1, so it ends up just being the force times the distance times 1. So what is the force? The force is also equal to the mass times acceleration. So you can change this equation to work equals mass times acceleration times distance. And then you can say that work makes you mad. But then you can also take the work and the mass and the distance and put them back in the equation, but change the acceleration to an equation that we get from the kinematic equations. This comes from the kinematic equations right here. And then this turns into an equation that looks like this eventually, with some more, the d's cancel out and just a little bit of rearranging here. You can turn it into this equation. And this actually becomes the equation that Émilie du Châtelet came up with. This is all her work right here. And this eventually led to Einstein discovering his equation, E equals mc squared. This is the same equation, E equals mc squared, just in a very different situation. So. Okay, so we call this the work energy theorem. This work energy theorem means that the net work done on a system, which is the net force times the net distance, or times the distance traveled in the direction of that force, is going to be equal to 1/2 the final velocity squared times mass, minus 1/2 the initial mass times the velocity squared. And that suggests that these two things are some kind of an energy, and that energy was given a name called the kinetic energy, or the movement energy. Kinetic means movement, so this means that there is energy that is associated just by moving. If you're moving, you have some energy that's associated with that movement. And this is actually well known, again, according to Émilie du Châtelet's experiments. When she was dropping those masses into the clay, she discovered that if you dropped a mass and it was going twice as fast when it hit the clay, it wouldn't go into the clay twice as much, it would go into the clay 4 times as much. And that's because of the squared. If the velocity is squared, it has 4 times as much energy. Because twice the velocity, if you have twice the velocity, it's 4, and square of 2 is 4, there we go. And you get twice as much energy, right? And this is one of the reasons that, speeding on the highway can be extremely dangerous. At 75 miles an hour, we're at kind of the limit of airbag safety. At 75 miles an hour, if you have all the newest airbags in your car and all the newest technology in your car, you can probably survive a crash at 75 miles an hour if you're wearing your seatbelt, and it's not too bad. If it's with another car on the same side of the highway or something like that. If you get into a crash at 75 miles an hour with older airbags and older equipment, you're not likely to survive no matter what you do, because it's just too fast. If you're going 80 miles an hour or 85 miles an hour, even with the latest airbags, you're not likely to survive. Because just a little bit increase in speed increases your energy a lot more than just a little bit. Your energy goes way up, and energy is the thing that causes damage in an accident. So, translational energy or movement energy, kinetic energy is what we call this. So how do you calculate kinetic energy of an object? You take its speed or its velocity in what direction it's going, multiply by itself, so you get squared, multiply by the mass of the object moving, and multiply by 1/2, and you get the kinetic energy of an object. If you want to calculate the work on an object, when it changes from one speed to another speed because something pushed it or pulled it, then you take its final kinetic energy and subtract its initial kinetic energy, and that will give you the work that was done on that object. And this does care about which one is first. It's the final minus initial, because it could show up as a negative or a positive either way. You can take energy from the system or put energy in the system. If you speed up the object, then obviously you put energy into the system, positive work. If you slow down the object, then obviously you're taking energy out of the system. In this case, we're going to take energy out of the system. We're going to have a package on a roller belt. We're going to push the package. No, actually it's going to have some initial speed, 5 meters per second. Sorry, 0.5 meters per second of initial velocity. And we're going to calculate its kinetic energy really quick. So the kinetic energy, 1/2 mv squared, pretty simple, 3.75 joules. And then we're going to calculate how much work it is required to accelerate the package. We have a 30 kilogram package. It's going to have a constant force of 120 newtons over a distance of 0.8 meters. So here's your force, here's your distance. They're in the same direction the package is going to move, so it's going to get a cosine of 0 degrees, which is 1. And then we're going to have an opposing force on there of 5 newtons. We want to calculate the net work done on the package. So the net work is the net force. So you have 120 newtons minus 5 newtons times the distance, 0.8 meters, and that's what they do right here. 120 newtons minus 5 newtons, that's 150 newtons times the 0.8 meters. There's your net work done, 92 joules. And then in part B it says, where does it say part B? Oh, same problem as part A, this time finding the work done by each force contributes to the net force. So they're going to do the work done by the force that is pushing it, 120 newtons, 96 joules, and the force that is resisting it, which is going to be a negative 5 newtons because it's in the opposite direction. So it's negative 4 joules. When you add those two together, you get the 92 joules that we actually ended up with. Now we're going to use this, the work energy equation. We want to find the speed of the package after it's been pushed. Well, we know the initial speed. They told us the initial speed was 0.5 meters per second. So that would go in here for V naught. We would have to square that eventually. The mass of the package goes in each spot, and we know the work done from the previous problem. So we put in all the numbers we know and we solve for the final speed. Or they solve for the final speed first, or the final velocity first. And when you solve for the final velocity, you get this equation that you can plug your numbers into, and you get 2.53 meters per second after it's been pushed. You can also figure out how far it was pushed, because once you know all the work that's been done, and you know the work that is being done by that, you know the force that's causing that work to be done, then you can figure out how far it's going to go. In this case, they want to know how far does the package coast after the push. So we know what it's, let's see, we know, in this case, we know how much work or how much energy is in the package. So right here, how much kinetic energy. Here we go. The kinetic energy of the package after it's been pushed is 3.75 joules, right? Let's see where we... Okay. So, which one are we using here? Oh, here we go. So here is the previous, in the previous problem we actually calculated the kinetic energy of the moving package, which actually is 95.75 joules. All right, so that's actually the total kinetic energy of the package. In this one, we were calculating. So this is the kinetic energy of the package when it's at 0.5 meters per second. This is the kinetic energy of the package right here, 1/2 mv squared final, when it's after it's been pushed. So 95.75 is the kinetic energy of the package. And we want to find out how much, how far it's going to go if we take all of that kinetic energy and remove it from the package through friction. Well, Work equals force times distance, so work equals frictional force times distance right here. The work that friction does is equal to force times distance times the cosine of the angle. Since the friction and the distance are going to be in opposite directions, and they're parallel but in opposite directions, then it's the cosine of 180 degrees, which is a -1. So it ends up being negative force times distance. Then we solve that for the distance. We get the distance equals the negative work done by friction over the frictional force. They told us the frictional force is 5 newtons, then we just do the math. You get 19.2 meters of distance that it travels as the friction tries to slow it down. So this is the energy that it gains by being pushed, and that's also the amount of energy, this plus the amount that it had to start, which is 3.75. So 92.0 plus 3.75. This is what it had when it had 0.5 meters per second of velocity. This is what it gained by being pushed. So this is its total. And all of that energy has to come out for it to stop, because all of this is movement energy. It's all kinetic energy. If you take all of that energy out by doing by letting the friction do this negative work on it, then it's going to be negative 95.75 over the 5 newtons of frictional force equals the distance, 19.2 meters. That's a long time, a long ways, actually. A long distance. Okay, so that gives us 2 types of energy so far that we've learned about. First type being work, which is energy done by force that moves. So if you apply a force to something and you move it in the direction that you're pushing or pulling, then that's work. If you are already moving, you already have some movement to you, then, and it doesn't matter if anything's applying a force or not, if you're moving, you already have energy that is associated with that movement. We call that kinetic energy. Now there is another type of energy which we call potential energy. Now potential energy is really exactly what it means, exactly what it sounds like. It is energy that you could have, but it's more like energy that can be converted into kinetic energy or can be converted into work, right? And so one of these types of potential energy is the type of energy that you get when you lift something up in a gravitational field. So the cuckoo clock is a classic example. On the cuckoo clock you have this mass, and it goes up on this chain through the clock, and inside the clock it's connected to some wheels and cogs and other things so that it makes things turn inside the clock as gravity pulls it down. Gravity is pulling on this weight and pulls it down through the day, and it turns the wheels in the clock, and that's what makes the cuckoo clock go. It's very similar in a grandfather clock where you lift up the masses to the top of the clock and then let them fall down, right? When you lift this mass some distance, or some height in this case, we usually call it, then it gains an amount of energy equal to the mass times the height that you've changed, that you've lifted it, times the gravitational constant, 9.8 meters per second squared. So it has that much potential, gravitational potential energy, mgh. And usually we write potential energy as a change, so the change in potential energy, because it always depends on somewhere where you started and somewhere where you finished. You know, we could all increase our potential energy by going up, but we could all decrease it as well. Even if we're standing on the ground, we could go to California and stand on the ground and we'd be 2,000 feet lower than we are here, right? So we have a lot more potential energy than people in California do, because they're closer to the center of the earth, essentially. They have less distance to fall, essentially. So this is another type of energy which we call potential energy. But it does depend on where you're calling the 0 point. If you're calling the 0 point the ground in Nebraska, then people in California are going to have a negative height. Their height is going to be considered negative, and they're going to have a negative potential energy. So you can have negative potential energy. You can have positive. It just depends on where you consider the 0 point to be. And every problem, you're going to have to choose a 0 point and stick with it. And it doesn't matter where it is. Sometimes it just makes sense to pick a certain point, but Once you pick your 0 point, measure all your height differences from that point, either up or down. Up for positive, down will be negative in most cases. So here's that example that I talked about earlier where we have things moving upstairs or things going straight up instead of going upstairs, right? If you're carrying this television step up the stairs, up the stairs, up the stairs to try to get up here to the top flight, what's the difference in energy change and the potential energy change if you just lift it using a pulley up to the top there? And it turns out that they're the same. Doesn't matter. Because all that really matters is the change in height. That's what changes the potential energy of the television. Also, that potential energy tells you how much energy you would gain if you fell from that height. So in this example, we have a 60 kilogram person who's jumping to the floor from a height of 3 meters, about 10 feet. If you land stiffly, then your knee joints will compress about a half a centimeter. What would the force be if this was the case? Well, work is equal to force times distance, and the work done is going to be done by your knees. Your knees are going to do some work to stop you. And the distance is going to be the distance that your knees compress. And we're going to calculate how much force is done. So we're going to rearrange this equation for the force. We have work equals negative force times distance because the person is going down, but the force is going up, right? It's stopping them. So that's fine, so it's just negative force times distance. But what is our how are we going to calculate this difference? Let me see here. Well, the way we're going to calculate this distance or this difference is by recognizing that the amount of kinetic energy that we're going to gain is going to be equal to the amount of potential energy we lose. As we fall through the air, we're going down in potential energy, but we're going up in kinetic energy because we're speeding up. Essentially, potential energy is changing into kinetic energy when we jump from a height and start falling. And this equation right here is pretty important. It says that this one right here, saying that the kinetic energy that you gain is always going to be equal to the negative of the change of your potential energy. So it could actually be a gain or a loss either way, depending on what the sign of your change in potential energy is. But the kinetic energy is always going to be equal to the negative of the change of the potential energy in the situation. In our case, it's mgh for the height being 3 meters, the mass of a person being the 60 kilogram. So we go from this equation, work, to this equation, to our work energy equation, which says that work is equal to kinetic energy, essentially the change in kinetic energy, our initial kinetic energy being 0, and our final kinetic energy being just the kinetic energy. And then if that is the case, then our work is equal to force times distance, and our work is equal to mgh. So we just set those equal to each other. Negative force times the distance equals mgh. Then we can solve for the force. It equals the mass of the person times g times the height that they jump from, divided by the distance that they stop in. So this distance and this height are not the same number. The height is from where you jump from. The distance is how much distance it takes for your body to stop. So you land, and then your knees compress, and then you're stopped. So that's the 0.5 centimeters. Plug all that stuff in, you get 353,000 newtons. That's a lot of force. And if you've ever jumped from a 10-foot tree onto the ground, stiff legs, you know it's a lot of force because you probably went to the hospital with broken shins. Okay? That's how much force there is. It's easily enough to break people's legs. However, if you bend your knees when you come down, here they have a great example of a kangaroo. If you bend your knees as you come down, then you increase that distance. Because you increase the distance, if you increase the distance, then you can decrease the force, right? And this actually gives rise to another reason that boxers roll with the punches. When you try to hit a boxer, if they just cringe up and tighten up their face and their muscles, then the impact time is going to be very short, which means the distance is going to be very short, which means the force is going to have to be big. But if you turn and let that punch hit you for a longer distance, in other words, you spread that distance over a longer distance, then the force actually can be smaller for the same amount of energy transfer. So it'll be a smaller force over a long distance, but it will be easier to handle. Now, how do we apply all this stuff in the real world? This is a great way that it's applied because roller coasters are fun. So if you've ever been on a roller coaster, you know that they lift you up to the top of the hill and then they just let you go. There's no power in the roller coaster after they take you to the top of the hill. It's just using gravity to do its work. And the reason for that is because at the top of the hill you have lots of potential energy. Very little kinetic energy because you're not moving very fast there. But that potential energy at the top is going to turn into kinetic energy as it goes down. You go really, really fast. At the bottom, your energy will all be kinetic energy. You have very little potential energy. And then you can go up and down and use all that energy to just move and move and move and move. In this case, they want to know the final speed of the roller coaster here, even if it goes down below here. And it turns out the equations don't care as long as there's no friction involved. And they're going to assume that there's negligible friction. So as long as there's very little friction involved, all you need to know is your beginning height and your final height, and your beginning velocity, and you can find your final velocity pretty easily using this equation where the change in the potential energy is going to equal the change in the kinetic energy. And this is giving rise to a new equation, a new energy equation where potential energies and kinetic energies are in the same equation. Essentially what's happening is you're trading back and forth. Well, the change in potential energy, it starts off at the top of the hill, ends up here at the bottom of the hill. We're going to call this top of the hill, we'll call this height equals 20. The bottom of the hill, well, this hill right here, we'll call height equals 0. And so that means our final potential energy is 0 because mg times h0 is going to be 0. And our initial kinetic energy is, our potential energy is what it is at the top of the hill, which is mg times the height of 20 meters, or whatever it is, 20 meters. That equals 1/2 the mass times velocity squared. We're going to solve this equation for velocity. Get square root of 2 times g times h. Plug it all in, get 19.8 meters per second in the end. And that's way easier than trying to do this with kinematics and forces. Doing this problem using forces and kinematics can be extremely painful. But this is just, I mean, we used one equation, rearranged it, plugged in, done. What if it wasn't starting from velocity of 0? If it started off at the top here going 5 meters per second or 0.5 meters per second or something, if it had initial velocity not equal to 0, then you'd have to change the equation a little bit, and they do that in this next section, where under the square root you would have a 2 times g times h plus the velocity initial squared. And it just changes like that. So if it starts off with 5 meters per second of velocity, you'll end up at 20.4 meters per second instead of the original, which was 19 or something like that. Okay. 19.8. So if it started off at 5 meters per second, it only increases by about 0.6 meters per second total at the end, which is kind of interesting. So potential energy can be changed into kinetic energy. Kinetic energy can be changed into potential energy. As you're moving along that roller coaster, if you go back up a hill, you slow down. And where does that energy, that kinetic energy go when you slow down? It goes into getting you up the hill, which increases your potential energy. So potential energy, kinetic energy can trade energy back and forth pretty easily, pretty readily. It's already 5 o'clock, holy moly. Let's see, this is section 4. Okay, so what we're going to do is we're going to split this chapter into 2 parts here. We're going to talk about in this next section, and then we're going to save 7, 5, 6, and 7, 8, and 9, the last 1, 2, 3, 4, 5 sections, we will save for Wednesday. These last two are very hard to do. This one's not terrible. These next two we'll do next Wednesday. So, conservative forces. Now, there's something that scientists are always looking for when they're doing their research and their studies. They're trying to look for things that stay the same in nature. When things stay the same in nature, that's when you can start building equations to describe them, right? Conservation is a type of thing that happens in nature where things stay the same. Conservation is an idea where you have so much of something and it can neither be destroyed nor created. It can just be moved around. And that is the case with energy up until this century. In this century, we discovered that energy is not truly conserved. It actually can be completely, it can disappear and become something else. It can become mass, in fact. And that's what the equation E equals mc squared is all about. But we're going to ignore that for now because it's beyond the scope of this class. And we're going to say that energy is conserved in the situations that we're going to be dealing with. As long as the forces are conservative forces, that means as long as the forces don't change the energy into something that is difficult to retrieve. Like friction, when it changes energy, what does it do? It changes like movement into something else. You know what that is? Let's make some friction. Put your hands together. Now put your hands together. Now make some friction like this. What do you make in between your hands? What's there, obviously? What do you feel? Heat, right? Heat is another form of energy. So friction turns movement energy into heat energy. And heat, when you take your hands apart, what happens? It goes away. It's actually heating the air, and it escapes in the air, and then it's almost impossible to capture again. It travels through the air in the room, it heats up the wall, and then the wall heats up the beams in the wall, and it goes through the roof, and then it goes out in the atmosphere, gets, scattered around out in the atmosphere, leaks out into space, goes on to the next galaxy. It's almost impossible to get that back. That energy just wanders away, and it's difficult to capture, difficult to reuse. Okay? So friction is what we call a non-conservative force. It doesn't allow the energy to stay in the system very easily. Okay? So if something involves friction, we're going to consider it not a conservative system. But if something doesn't involve very much friction, we can consider it conservative. And one of the things that doesn't involve very much friction are objects falling in gravity, as long as they're not falling too fast and as long as they're not falling a very long distance. So if I drop something like a bowling or like a billiard ball, like a pool ball, just drop it from here to the floor 1 meter or so, there's going to be very little friction on that ball. Very little air friction, very little anything. And it will behave almost like it's conserving all the energy. All the potential energy will become all the kinetic energy, and you could measure those things and they would be very close to being equal, and it would be great. Another thing that does fairly good job at conserving energy are springs, but again, it's only small springs and small distances and small masses. Once you start to get into bigger things, the springs start to heat up, and you can really notice it. And then once you heat things up, then you struggle with keeping it conservative. But in a spring, sometimes things are sometimes they have conservative forces. So we have to talk about springs for a little bit. We've already talked about the force that is involved in stretching a spring. It's equal to the mass or it's actually equal to the distance that it is stretched times spring constant, k times x. And if you continue to stretch a spring and you put this on a force distance diagram, which remember is an energy diagram if you measure the area under the curve here. This is what the force times distance curve looks like for a spring. You keep pulling on it, and you have to pull harder and harder to move it more and more and more. So it looks kind of like a triangle. And if you measure the area under here, the area is equal to 1/2 kx squared, which is actually going to be equal to the potential energy stored in the spring. So if you stretch a spring, it has potential in it. How do you know it has potential? How do you know you have energy stored in a stretched spring? What do you do to see if there's energy in the spring? Don't you let it go? Right? If you stretch a spring and then let it go, you'll know there's energy. It'll bounce back, it'll pop somebody in the eye, it'll do whatever it does. There's energy in the string that's stretched. In a compressed spring, it's the same way. If you compress a spring and then let it go, it goes poing, and whatever it's touching is going to push on it. It has the ability to do things. So potential energy is stored in a spring when you stretch or you compress at a certain distance. And that distance is x, and if you want to know how much energy is in that spring, you have to know the spring constant, so you have to have measured something about that spring, your k. And it's the distance that you stretched it or compressed it squared times k times 1/2. And that gives you the amount of energy stored in the spring. So now we have energy stored in in a couple of different ways. So we've got energy can be stored in the height that you lift something above the ground, because if you lift it above the ground, you can let it go and it'll fall. You lift it up a hill, you let it go, it'll go down the hill, whatever. But we also have energy that we can store in stretching or compressing a spring, because if you let go of it, it releases that energy. But there's also energy in movement. It's kind of like it's stored inside of moving objects as well. Kinetic energy is like the energy that is part of movement, right? But there's also energy when you apply a force to something. There's energy transferred between the thing pushing or pulling and the thing being pushed and pulled, right? So that's work. So 4 kinds of energy. I shouldn't write them on the board. I should put them on here. Whiteboard. So we have 4 kinds of energy so far. We have work, right? So work is all about push or pull over a distance. Man, it's terrible writing. Right? And work is equal to the force times the distance times the cosine of the angle between them. You have a force this way, and you have a distance this way, for example. If you're pushing it this way, but it moves this way, then the angle theta between them you have to put into the equation, right? So that's the first kind of energy. We have the second kind of energy is kinetic. Kinetic energy is movement energy. Movement energy. Anything that is moving has kinetic energy associated with it. And to calculate kinetic energy from our friend Emily du Châtelet, 1/2 the mass times the velocity of the object squared. Notice that this one has this squared thing in it. Can kinetic energy ever be negative? Can you think of any numbers you could plug in here to make it negative? Because work can be positive or negative. Can this one ever be negative? Can you ever have a negative mass? Can you have a negative velocity? Sure, you can. Depends on which way it's going, right? If it's going this way and we're calling this way positive, then it's going that way, it's positive. If it's going the other way, opposite way, it's negative. But can you ever square a number and come out with a negative number? No. So it doesn't matter if the velocity is negative, it's still going to end up with a positive number in kinetic energy. This one can only be positive. Only positive numbers for kinetic energy. The third type is gravitational potential energy. I'm going to call it GravPot. There we go. And that is essentially energy stored in height. Right? Stored by lifting, you can think of it as. And that's potential energy mgh. And this one is important. You have to choose where h equals 0 is going to be, where your 0 point is going to be. And then h can be either above that or below it. And h can be positive or negative. So that means that potential energy can also be positive or negative. Gravitational potential energy. And then the last one we've done is spring potential energy. And this is energy stored in a spring or some kind of springy material. Man, that's terrible. And that is, so we call this one potential energy gravitational with a little g down here. We call this potential energy with a little s for spring. 1/2 kx squared. Where x is measured from the relaxed length or from the middle point of the spring. Think of it as measured from equilibrium point to the relaxed length. Now, what is the point of writing all these down? You can have all kinds of situations where all of these are involved. For example, you could have a car rolling down a hill. It's starting off with some kinetic energy, but it's on a hill, so it has some gravitational potential energy too. Right? And as it's rolling down the hill, its kinetic energy is increasing because its gravitational potential is turning into kinetic energy. And then at the bottom of the hill, it hits a big spring that stops it. So the kinetic energy of the car turns into spring potential energy in the spring. And then the spring re-releases that energy and pushes the car back and pushes it back up the hill. And the spring does some work on the car and gets it accelerating and goes up the hill, and then gravity does work on the car. I mean, you have all kinds of things. Energy can get passed back and forth and back and forth and back and forth and back and forth. You could have friction doing work on the same problem. You have all kinds of things. The energy can kind of, you have 10,000 joules that can, 5,000 of it can become gravitational potential and 5,000 of it can become kinetic energy. That means half of the energy would go to speeding up the car, and half of the energy would go to getting the car up a hill, or something like that. Right? So these energies can go back and forth and back and forth and back and forth, and there are many, many examples of this in the homework and in the book. So let's look at an example of this right here. So what does conservation of energy look like now? We had these other equations before, but now, if you do work on an object, you can change its kinetic energy. But if you do work on an object, you can also change its potential energy. You can also change its height. And it turns out that if you change the potential energy and the kinetic energy changes because the potential energy changes, then the kinetic energy and the potential energy are going to equal negatives of each other. Which means if you solve this equation, put everything on one side, you get the kinetic energy plus potential energy equals 0. And if you split up these deltas into finals and initials, you get this equation. And this is what we call the conservation of energy equation without friction for conservative forces only. So if you don't have any friction, you can use this equation to solve for anything you want. And you can include in this equation the spring potential energy as well. So you can have kinetic energy initial plus potential energy of spring plus potential energy gravitational. You can have 3 things on each side. So here's a classic example of this. Lots of people love this one. We have a car that starts here, and the spring is compressed, and then it releases the car. And this compressed spring gives all of its potential energy to the car to make the car move, which means potential energy in spring becomes kinetic energy in car. Then the car goes up a hill, which means kinetic energy in car turns into potential energy of car, right? Or it could go down through here and go through the loop-to-loop and go back up to here. But it turns out it doesn't even care. Because if it goes down here, it gains energy by going down the hill, it gains kinetic energy by changing potential energy, loses it, it goes back up here, and then loses it, it goes back up here. No big deal, it has the same thing at the ends, same result at the end. We'll start at the same height, we'll end at the same height, start with the same spring, end at the same height. So how do you do this? You set up a conservation of energy equation, your initial kinetic energy plus all of your initial potential energies, that includes gravitational and spring potential energies, equals your final kinetic energies plus all your final potential energies. So what's your kinetic energies? 1/2 mv squared, initial velocity squared, 1/2 mv initial squared. Your original potential energy gravitationally is mgh initial. So what is an initial height here? It could be 0 or it could be 12, it could be whatever you want it to be. In this case, they're choosing this to be 0, and then this ending height would be 18 centimeters above it. So this one, because this one is 0, this term is going to end up equaling 0. And then 1/2 kx squared is going to be how much potential energy is in the spring to start with. Well, that's how much spring energy you have right there at the beginning, and that spring energy is going to be important, because right up here they tell us that it is a spring constant of 250 newtons per meter, and it's compressed 4 centimeters. That's your x, that's your k, for 1/2 kx squared. And then you have a final kinetic energy, a final height in potential energy, so you're going to have a final gravitational potential energy. And there's no spring at the end, so you don't have any final spring kinetic energy. That's going to become 0. In the end, this is what your equation looks like. You solve it for your final velocity, and you are able to plug in the numbers and get a value. It's pretty simple. Oh, actually, this is not for the speed at the top of the slope. This is for the speed right after it leaves the spring, because they don't give you any potential energy at the top. I just noticed that. Here, the potential energy at the top is 0 because you're going from spring compressed to spring uncompressed, and the car is right in front of the spring. So that's why that mgh right there is 0, and you can solve for that velocity. Gives you 2 meters per second. Now you could do that using the force the spring exerts as well. You could do it using kinematics and dynamics, but this way is easier. It's one equation, solve it, be done. And there's no vectors, there's no kinematic equations you have to solve 2 unknowns for or anything else. Just one equation, done. But then they want to know what it's going to be at the top of the hill. So if it's at the top of the hill, you use the same equation, but your beginning potential energy is 0, but your final potential energy is not. Everything else is the same, so you end up with an equation that looks like this. We have a final potential energy at the top of the hill with height final. So then you solve this equation for your final velocity. You get a different solution, and you plug in your numbers, and you get a different answer at the top. It's going 0.687, and you'd expect to be going less when it went to the top of the hill, and it is. At the bottom of the hill, right after it comes off the spring, it's going 2 meters per second. At the top of the hill, after it's come off the spring and gone up the hill, it's going less than 1 meter per second, which makes sense. So, that is the idea behind these problems. Simply put, without getting into the idea of, well, we could actually do one more section. We've got time. It's only 5:10. Let's do one more section. What happens if there is friction involved? If there's no friction involved, it doesn't matter what path you take from A to B, because the friction is not going to remove any energy, and all it cares about is how far you moved in some kind of situation. It essentially wants to know how, your beginning and ending position in height, and then everything else is a matter of conservative forces, no worries. So here is a system which has a spring in it, and this is going to be more of a realistic spring. You drop a rock on the spring, and the spring compresses, and essentially what happened is you have potential energy turns into kinetic energy. Kinetic energy turns into spring potential energy. Spring potential energy turns back into kinetic energy, shooting the rock back up again. And then you have kinetic energy and potential energy at the end as the rock is going back up to its original position. If there's no friction involved, this will end up at the same height it stopped at, and it will have only gravitational potential energy. It will stop at the same height that it started. Right? Have no kinetic energy, and end up where it starts. But if there's some friction in the spring, so if the spring heats up, if there's some friction with the rock in the air, then you're going to be losing energy at every point along this path. In fact, the more times you bounce up and down on the spring, the lower it's going to get, which is exactly what you see in real life, right? You bounce a ball and it gets lower and lower and lower every time. And that's because of friction and non-conservative forces. So the longer the path it takes, the more energy it takes out. If you just drop a rock straight down with no spring, of course it doesn't bounce hardly at all, unless it's a really bouncy rock on a really bouncy ground. But it makes some heat. It makes some heat from hitting the ground. That makes some sound. That's another way that you can lose energy to their surroundings. It's very difficult to get it back. And also maybe it breaks the rock, or it makes a hole in the ground or something like that. All those things are manifestations of energy that are very difficult to regain, to put back into the system. So when you do have forces or things in your system that are non-conservative, they have to become part of your total work that's done. So your network has to become the work done by conservative forces like gravity and springs, and then the work done by non-conservative forces like sounds and breaking of things and friction and stuff like that. So in the end, you get your non-conservative work plus your conservative work equals your change in kinetic energy, right? But then the conservative work is just going to change the height, it's just going to change the potential energy. So then you get the work non-conservative equals kinetic energy plus change in potential energy. And then you can actually solve this by splitting up your changes in kinetic and changes in potential into initials and finals, putting them on either sides of the equation. And you get this, your initial kinetic plus your initial potential plus your initial non-conservative work, initial kinetic plus initial potential plus all of the non-conservative work on the left side of the equation has to equal your final kinetic energy plus your final potential energy. And what this means is that you start off with some energy in your movement, some energy in your speed. You start off with some energy in your height or in your springs or whatever else. And then some of this energy is removed by friction eventually. And when that energy is removed by friction, you're left with this. Right? That's kind of what this equation means. So here's an example. I'm going to talk through the example without doing the math first. You have a person who's sliding into a base, right? As they slide, they lose speed, which is kinetic energy, right? They lose kinetic energy because they're sliding on the ground, which is friction. So non-conservative work is taking that energy out of kinetic energy, right? So how do we do this problem? The work equation says that initial kinetic energy plus potential energy initial plus non-conservative work equals final kinetic energy equals final potential energy. Well, the potential energy at the beginning and at the end is the same because it's a flat field. They're not moving up or down, right? So if it's a flat field, the beginning and the end, same potential energy, they cancel out. Then you're just left with your kinetic energy initial and your final kinetic energy and the non-conservative work on the left side. And that's the equation they have right here. Right? This is their kinetic energy when they're done. When you're done sliding, you're stopped, right? So you have no kinetic energy. This is your kinetic energy when you start sliding. We'll have m and v initial squared. And this is the friction done, minus the force times the distance. The force of friction times the distance is the work done by friction, and it's always a negative. Then you solve for the amount of friction. We're actually going to solve for the distance d by putting everything on one side except for the f and the d, and then divide by f on both sides. And you get the amount of friction done, and you can calculate it. We have not done a problem here yet that involves more than one equation. Right? There's maybe a lot of things to plug into it, but it's just one equation. We've also not done an equation that requires vectors. This is great. What if you're sliding up a hill? If you're sliding up the hill, then your potential energy is going to change, and these have to stay in the equation. You have to change your height, right, as you're going up the hill. So instead of having a zero potential energy on both sides, or the same potential energy on both sides, you may start at the bottom of the hill, so you have zero potential energy. But at the top of the hill, you have some potential energy, mg times the height, but the height is the distance that you slid, which is the hypotenuse of the triangle, times the sine of the angle, which would give you this side, so d sine 5 degrees. So they plug that in for sliding up a hill. Then everything else is the same and solve for d. 2.31 meters of distance. So you go less distance if you're sliding up the hill than if you're sliding on a flat surface, which makes sense again. Sliding up a hill, some of your energy is used to go up the hill instead of all of that energy being used to go against the friction, right? In this last part, they tell you that you can actually measure the distance that you've slid, and then you can calculate how much friction. Or you can measure the distance, and if you know how much friction there is, or there's supposed to be, you can calculate their initial speed. And that's how police officers measure the skid marks on a road and determine how fast somebody was going before an accident happens. And we'll actually get to that next time. We'll do some of that next time. So I'm going to leave it there, and we'll come back to this next time. So get finished with chapter 6. I didn't get to any questions. I noticed there were a bunch of questions in my open math, but I didn't get into answer any of them yet. So if you had any questions in there, I'll try to get them answered today or tomorrow. And then tomorrow we have lab. Wednesday we'll be answering questions for chapter 7. And chapter 6 also, since chapter 6 won't due till Wednesday, right? When is chapter 6 due? Forgot. Well, it's due tonight. Okay. So we should probably make that due tomorrow night in case you have any more questions. And then we'll, if you have any more questions tomorrow, after lab or before lab, you can ask those questions. But I'll try to answer all those questions today and tomorrow online so that you can have your answers for those before that's due. And then we'll finish up chapter 7 on Wednesday, have that due on Friday. Sound good? Any homework questions, any more other questions or any kind that you have? Yeah. Everybody did the exam already? And I will go through and recheck the exam to make sure that you didn't give a good answer that just wasn't accepted because of some goofy little thing that you didn't do. I'll make sure that that's the case. Let's see here. This one? like that, right? So solving for, which one do you want me to solve for?
I think if I can solve for a
A sub x?
yeah.
Okay. So for solving for a sub x, we want to get this thing by itself first. So I'm going to subtract this thing from both sides, vx0, vx0. Get a new equation, vx minus vx0. Here they just cancel out, equals axt. Right? Divide both sides by t. And there's your final answer. Now to put that into MATLAB, it looks like this. If you wouldn't have to write the a sub x, but a sub x would look like this, a sub x. And that would equal, and I would put in parentheses, v sub x minus, then I would do v sub, oops, v, I would do a sub and then parentheses, x times 0, or just x0, like that. And then another parentheses and divide by t. So if that didn't work out for you, just send me a note and I'll take an extra look at your test to make sure that it didn't just say, you know, the syntax was bad because of some dumb thing. Like if you put a capital V accidentally or something, that happens and I don't care. I will mark you down for that. So, did that make sense? Any other questions?
I have a question on 13 on chapter 6.
13 on chapter 6.
Yeah.
Okay. Okay, so they're gravitationally attracting planets. They give us the mass of planet A, the mass of planet B, and the force pulling them together. They want to know how far their centers are separated, right? So we have planet A, which has mass A. We have planet B, mass B. We have the distance between them. No, we don't have the distance between them. We have the force between them. We want to know what D is. And we know that the force between them is force whatever, right? Well, the general gravitational equation says that G, the force due to gravity is equal to the big G constant times the mass of the first planet, which would be mass A, times the mass of the second planet, which would be mass B, divided by the distance squared between them, and we want to know the distance, right? We know this one, this is a constant, we know that, we know this one, we know this one. This is the only one we don't know. And that's what we're trying to figure out. So we solve it for this. Now, when you're dealing with a fraction on one side of an equation that you're trying to solve for something, and the thing you're trying to solve for is in the denominator, there are a lot of different ways to do this. Some people like to do what they call cross multiply. Some people like to do other goofy things. What I'm going to do is I'm just going to multiply everything on every side by the stuff that's in the denominator. And that's just going to get rid of all the denominators. Right? So if I multiply this side times d squared and this side times d squared, then the d squareds over here go away. And I'm left with d squared f equals g m a m b, right? And I want to solve for d squared, so I need to get d by itself. I want to solve for d, rather. So I'm going to now divide by f on both sides. And that's going to get rid of the f on the left-hand side. Now I have an equation that looks like this. D squared equals g m a times mb over f. Then if I take the square root of both sides, I've got an equation. You're good. Any more questions? You good to go? Be done today? All right, we're done on time. Woohoo! Little early. Okay. Have a good day. We'll see you tomorrow. Do some experiments tomorrow. And we'll keep moving through this summer.